Hello everyone, welcome to my video for the SEG2020 annual meeting. My name is Yumin Zhao. I'm a PhD candidate in the group of Simple Geophysics project at NS. Beamforming is a useful technique to resolve the direction of the ambient noise wave field, and it's commonly applied to the ambient noise data recorded by the vertical component of the geophone. In this presentation, I will talk about the application of beamforming on dust data, analyze the reliability of the beamforming results, and finally, I will show you how to identify the wave types from the data using the directional information. Let's start from introduction. Seismic interferometry is a technique to extract spatially coherent seismic signal from the ambient noise wave field, which is assumed to be generated from uncorrelated, uniformly distributed noise sources, just like these red dots. By cross-correlating the ambient noise received by receiver A and receiver B for each azimuth, and then stack them, we can obtain a symmetric cross-correlation result. However, in the real conditions, especially in the urban environments, the ambient noise sources are not uniformly distributed. For example, this fiber in the red box was deployed nearly perpendicular to the major road. We can see the cross-cologram obtained from the data is asymmetric. For the Stanford dust array, the two cross-colorograms are obtained from the data recorded by the two legs marked by the red line. We can see the cross-colorograms are also asymmetric. Conventionally, in passive seismic, we use the ambient noise recorded by the vertical component of the geophone to image the near-surface structures. The processing workflow is like this. We first apply cross-correlation on the pre-processed ambient noise data to obtain the cross-cologram. Then we can apply beamforming on either the data or the cross-cologram to resolve the direction of the ambient noise wave field, and the apparent dispersion curve can be extracted from the cross-cologram. Next, we need to correct the phase velocities by applying the directional correction on the apparent dispersion curve. Finally, we can obtain the subsurface shear wave velocity model by inversion of Rayleigh waves, since the recorded data by the vertical component of geophone are Rayleigh waves. Dust has many advantages compared to geophone, especially for the monitoring purpose in the urban environments. Generally, the processing workflow of dust data is the same with that of geophone data. However, there are two problems when using this processing workflow. The first one is beamforming results may not be reliable due to the amplitude projection and polarity reversal in the data. Amplitude projection is caused by the directionality of fiber optic cable and the geometry of the dust array. Polarity reversal is usually caused by the nonlinearity of the dust array. The second problem is that it's hard to identify the wave types and their proportions in the data. Because the optical fibers are usually deployed horizontally, it will record both Rayleigh and love waves, and this will make the inversion process much more complex, since the forward modeling of Rayleigh and love wave are different. Looking through other studies on near-surface imaging using dust data, we can see in real cases, most of the cross-colorograms are asymmetric. However, there is no study applied directional correction on the extracted apparent dispersion curve, and there is no analysis on the wave type in the dust ambient noise recordings before inverting for the subsurface shear wave velocity. There are two cases using beamforming on the dust data to resolve the mean propagation direction of the source wave field. However, the dust data they are dealing with were generated from a unique source. Application of beamforming on the dust ambient noise recordings will be more complex, since the polarity reversal cannot be directly identified from the data and there is amplitude projection in the data. Since we intend to invert for the subsurface velocity model from the Stanford dust data, the first step is to solve these two problems. The first one is explore the reliability of beamforming on dust ambient noise data and resolve the direction of propagation of ambient noise sources from it. Use this information, we can correct the apparent phase velocities. And the second one is identify the wave types in the data. If there is one type of surface wave dominant, we can choose the corresponding forward modeling and invert for the subsurface velocity model. However, when there are two types of wave mixed together, we either need to separate the two waves or invert for the velocity model using both relay and lab wave. Now let's see the methodology. To explore the reliability of beamforming, I first did some synthetic tests. The layout is the same as the Stanford DAS3. The intersection angle between these two legs is 85 degrees. This figure shows the phase velocities used to model the data, and they are obtained from the shear wave velocity model published in Speca et al. 2020. We use the Rayleigh wave phase velocity to model both the vertical displacement and the Rayleigh wave strain rate. All the data are modeled using random sources. NS is the number of sources, and AI is the amplitude of the I source, and it's random. Theta I is the direction of propagation of the I source, and capital A is the amplitude spectrum obtained from the real data. Rayleigh and lab wave strain rate are obtained by averaging the pointwise strain rate in a certain range called gauge length. From the DAS ambient noise equations, we can see that if the array is in L shape, there is always no priority reversal in the Rayleigh wave strain rate, while there is always priority reversal in the lab wave strain rate. And for lab wave strain rate, there is always no amplitude projection. We use music beamforming to resolve the source directions. Music stands for multiple signal classification. It's a high-resolution beamforming technique. The main idea of music is that it decomposes the signal into its main components by performing singular value decomposition on the top-list matrix R here, and UL contains the eigenvectors obtained from the decomposition. Together with the array plane wave response S, they can construct the beamforming spectrum P. The peaks in the music spectrum represent the ambient noise wave field direction and velocity of propagation of surface waves with multiple frequencies. Generally, phase velocity of lab wave is higher than that of Rayleigh wave. To identify the wave types, we extract the dispersion curves from the two lines perpendicular to each other and compare their phase velocities. Here we use the phase shift method to extract the dispersion curves. This is our processing workflow to resolve source direction and identify the wave type. We first apply amplitude normalization on the pre-processed data. Here we use RMS amplitude ratio. Then we can obtain the cross-correlograms using cross-correlation, and we can identify the priority from it. Then we need to apply priority flip on one leg of the cross-correlogram if there is priority reversal in the cross-correlogram. Next, we can apply beamforming directly on the cross-correlogram and resolve the source directions. Then we can correct the apparent dispersion curves using this angle. By comparing the phase velocities from the two dispersion curves, together with the amplitude information, we are able to identify the wave type in the data. Now let's see the synthetic data examples. We first did a synthetic test when there is only one direction of propagation of ambient noise wave field. The first column shows the synthetic vertical displacement, Rayleigh wave strain rate, and lab wave strain rate, when the incident angle is -5 degrees. You can see the amplitude projection is very severe in the Rayleigh wave strain rate due to the directionality of DAS and the geometry of the array. We cannot identify the priority in the data, but we can identify it in the cross-correlograms. We can see there is no priority reversal in the Rayleigh wave strain rate, and there is priority reversal in the lab wave strain rate. And these are the beamforming spectra calculated using the cross-correlogram obtained from the normalized data. We can see the resolution of the results are greatly enhanced. This slide shows the data contain both Rayleigh and lab waves, but with different ratios. The resolution of the beamforming results is also improved a lot after applying amplitude normalization on the data. When there are two directions of propagation of the ambient noise wave field, the two directions may not be resolvable from the vertical displacement, since the resolution of beamforming is limited. These are the two criteria of the resolution of beamforming. We can see the resolution is determined by the array aperture and geometry. From this example, we can see even if beamforming can resolve the two source angles from the vertical displacement, it's hard to resolve both angles from the DAS ambient noise. If the sources are uniformly distributed, the beamforming spectrum will highly depend on the geometry of the receiver array. For the vertical displacement, it requires more energy from the sources, perpendicular to the angular bisector of the two legs. For dust ambient noise, beamforming can only detect the signals coming from the directions along the angular bisector and perpendicular to the bisector. So from the synthetic tests, we can conclude that when the sources are all coming from one direction, beamforming can resolve the source propagation direction after we apply amplitude normalization on the data and remove the polarity reversal. But when there are two or more sources, the results may not be reliable. Now let's see the field data examples. The first row are two 100-second dust data recorded by the Stanford dust array on different days. We can observe the amplitude difference from the data. The data in the second row are normalized after preprocessing. From the cross-colorograms, we can see polarity reversal exists in both data. Then we calculated the beamforming spectra from the cross-colorograms after removing the polarity reversal. These results are reliable since the resolved direction is consistent with time-lag changes in the cross-colorograms. The source direction can be used to correct the apparent dispersion curves. Before inverting for the subsurface velocity model, we need to identify the wave type from the data. Since there is polarity reversal in the data, it must contain love wave. It may also contain Rayleigh wave, since there are amplitude differences between the data recorded by the two legs. But the differences may also result from the poor coupling condition. Intuitively, when it is love wave dominant in the data, the true phase velocities obtained from the two legs should be the same. We extract two dispersion curves from the two legs of the real data and plot them together. We can see the phase velocities in the east-west line is larger than that in the north-south line. So the data must contain Rayleigh wave, and love wave may dominate in the east-west line, but in the north-south line, Rayleigh wave may have a relatively high energy. We get the same conclusions from the data recorded on another day. This figure shows the relationship between the RMS ratio between the two legs and the Rayleigh and love wave ratio. We can see the RMS ratio changes monotonically with the Rayleigh and love wave ratio. From the beamforming results achieved previously, the source angle is minus 70 degrees. We model the data with different Rayleigh and love wave ratio and calculate the RMS amplitude ratio for each data. For the real data, we also calculate the RMS ratio using the two parts of the data labeled by the red box, and the ratio is this number. From the table, we can see this ratio corresponding to the case when the Rayleigh and love wave is 1 by 1.3. These two figures are the corresponding synthetic data and the cologram. We also did the same test for the data recorded on another day, and we got a rough Rayleigh and love wave ratio 1 by 1.6. Now let's move on to the conclusions. So there are two parts in my presentation. The first part is beamforming on dust ambient noise data. Different from the vertical component of geophone data, dust data has its own complexity, such as amplitude projection and polarity reversal, and this complexity may cause the unreliability of the beamforming results, and these are proved by our synthetic data examples. So we normalize the data using amplitude ratio and remove the polarity reversal from the data before applying beamforming to the data. And in this way, beamforming results are reliable when there is only one source direction. However, when there are two or more directions, it will be too complex and the results may not be reliable. The second part is wave type identification in the dust ambient noise data. It is very important to identify the wave types in the data before inverting for the subsurface velocity model so that we can choose a certain forward modeling scheme. Source direction information can help us to identify the wave types in the dust ambient noise data when there is only one source direction. And if the amplitude information in the dust data is reliable, we may be able to have a rough estimation of the Rayleigh and love wave ratio in the dust ambient noise data. And these are our acknowledgements. We thank Professor Biondi for inspiring us working on this problem and providing the data. We thank Dr. Fang and Dr. Martin for discussion, and thank our sponsor, Cambridge Sensing, and finally thank other developers of Madagascar. Thank you for watching my video. I welcome to your questions and suggestions.